Hello students, in this video we'll discuss about the principal sources of optimizations. So in the last video we have discussed about register allocation and assignment. So coming to the principal source of optimization, we have some optimization techniques which we have already discussed in the previous videos. See, other than that, what are the two things and how they are going to be? So here we are going to have constant propagation and code movement. So these are the only new things, and remaining all we have discussed already in the people optimization and global optimization. So that's what I'm trying to tell you guys. The concepts are redundant when it comes to optimization. See, maximum in all the videos whatever we have taken from the optimization, I can say the third video or fourth video, whatever it is. So we have discussed about this common sub-expression elimination. Somewhere we might be taken as redundant elimination, somewhere we have taken as okay, useless, right, whatever it is, but we have discussed this in everywhere. So same, even in exam also, if you get any questions related to the optimization, just remember the techniques whatever we have used, like 8 or 10 techniques. Then you can write, okay, just mention that where we are using it. If it is people, just mention that it is a block. If it is global, just mention that it is in more than one block, like that. So first we'll go with the compile time evaluation. So if you could able to perform some optimization before execution or at the time of compilation, then we can call it as compile time evaluation or compile time optimization. So there we are having two techniques. One is constant folding and another one is constant propagation, propagating the constant to the more than one basic block. That's the meaning of it, right? So let me first go with the constant folding. So here, so evaluates an expression with the constant operand to replace the expression with the single value. Right here, see guys, 22.0 divided by 7.0. These two are constant at the time of compilation. So we can evaluate this expression at the compile time and we can just replace it with the result. That is 3.14. This is called folding, right? And what does it mean by propagating? Replace a variable with constant which has been assigned to it earlier. Right, here we are evaluating the expression, but what we are doing here, for example, pi, assume that this variable is constant int pi, then 3.14, wherever you are adding the pi, that can be replaced with the 3.14, like area equivalent to, so in place of pi I just replaced with its current value, constant value. Now what is the advantage of it? See, if what is the advantage of this state constant propagation means, what does it mean? Propagating the constant to the variable wherever we are using it. What is advantage? So if it is a constant, you no need to go to the memory to issue some load instruction, right? So that we are going to reduce the cost, instruction cost from 1 to 0. Here we have to issue the load instruction to get the value of pi. But if it is a constant, you don't need to issue any, right? You can directly perform the multiplication operation with the r. So that is called propagation. And the difference is evaluating the expression is folding. Means what? The expression is folded to value. Propagating means propagating the variable constant to wherever the variable is occurred. The next one is common sub-expression elimination. Of course, this we have already discussed, right? So simply we have to identify the sub-expressions present in different expressions, compute once, and use the result in all the places wherever we are having. Right? A equivalent to B star C and X equivalent to B star C plus. So simply you can replace this B star C with the A, right? You can do in that way. But the problem with this, right? So for example, you are having B star C here, right? And we have A. Assume that, let me explain. This is 5 and this is 4. And what is the value of A here? 20. And same, the 5, 4. So B star C is nothing but 20 only. And instead of B star C, if we write A, then the A value is also 20 only. So nothing. The X value is remain unchanged. But when we can do such means, guys, here, if we have a common sub-expressions like this, so between these expressions, the values of A, B and C must not be changed. If it is changed, we cannot evaluate this expression. For example, remember this. Assume that the B value is 5 here, B value is 4, and what is A value? 20. And here we can write A value directly instead of B star C, but make sure that the value of A, B, C are unchanged. What will happen if it is unchanged? Assume that B value is 5, then in between these two, I've changed the B value to 10. Then what will be happened here? So 10 into C value is 4, C is not changed. That is 40 plus 5. Before optimization, what is the X value here? 45. But by thinking that B star C common sub-expressions and replacing this B star C with the A, what is the A value? 20. So 20 plus 5 is 25. These two are different. So before performing this common sub-expression elimination, make sure that in between these two expressions, the values of A, B, C are unchanged. Then only we can do it. Otherwise, you are not supposed to eliminate the expression. The next one is code motion. See, the code motion is nothing but moving the code from one basic block to another basic block. Means what? One place to another place. For example, if you are having like this, if A less than B, then we are performing X power 2, and here we are applying. Then what I'm doing here, I'm just simply moving this X power 2 and X power 2 out before this by computing it in a temp variable. Once we are computing and moving the code outside of the control blocks, then wherever you are using this X power 2, that we can use the temp. Then you may get a doubt, what does it different between common sub expressions and this? Here also we are removing it, but we are changing the place of that expression. Right? We are not writing here, we are changing it. Here we are not writing Z or something. So two codes we are moving. Right? Let me tell in another example. This we have already discussed in global optimization. So assume that while, okay, I less than or equivalent to 100. This we have discussed already. Like Z equivalent to X power 2 and I equivalent to I plus Z. Assume that. And the value of X is remain unchanged. Int X equivalent to 5. What it is? 25, right? Throughout the 100 iteration, the power no need to compute. Then you can move this code outside of it. Then you can write T equivalent to X power 2. Then you can write here T. So moving the code from inside to outside, so that we are reducing the computations of power here. That's the meaning of code movement. Next one, strength reduction. So of course this also we have discussed the strength reduction in some other right concept like people optimization. So simply replacing an operator with a less cost, right? Like I into 5. So I is 1 to 10. So simply this into 5 you can perform before it and you can do it, right? So then you can write temp into 5 here, or temp equivalent to temp plus 5. They are writing it instead of star 5, they are making it temp equivalent to temp plus 5. So automatically what will happen, instead of performing the modification every time, we are adding the 5. Okay, or okay, not only in this case guys. For example, as I told you now, replacing the high cost operator with the low cost operators. So if it is X equivalent to I into 16, then you can simply replace it with the X equivalent to I left shift. 16 can be replaced with the 2 power 4, then you can perform the 4 shift. So where we are going to use it in the address calculation of array references, we can use the strength reduction, right? Or some induction variable elimination, we can use it. What it is, we'll discuss in the next video. Induction variable elimination, right? So okay, let me go with the first. What does it mean by induction variable elimination here only? So assume that we have right, sorry, assume that we have a loop like this. While, okay, so I less than or equivalent to 5, right? I equivalent to I plus 1, and a of x equivalent to a of x plus 1, then x equivalent to x plus 5, right? Assume that. See, what is the meaning of it? Assume that I equivalent to 1. So how many times this loop will be iterated? 5 times, right? How many times this loop will be iterated? 5 times, because 1 less than or equivalent 5, 2 less than or equivalent 5, like every time we are incrementing it. So the loop will be iterated for 5 times. When I equivalent to 1, we are changing a of, assume that the x value is 0 initially. So a of 0 equivalent to a of 0 plus 1. We are incrementing the 0 value. When I equivalent to 2, then x is incremented by 5. Then we can take it a of 5 equivalent to a of 5 plus 1. Okay. Then when I equivalent to 3, a of 15 will be incremented. When I equivalent to 4, a of 20 will be incremented. When I equivalent to 5, a of 25 will be incremented. So what is the use of I here? Simply we are incrementing it. So the induction variable means throughout the iteration the value of a variable is incremented or decremented with fixed amount of time. So here what are the variables which are induction variables? Means I and also x, but not a, because a is every time changing, a1 0 like that. Sometimes we are changing a0 value, sometimes we are changing a5 value, right? Not single a value we are changing, right? But x is constantly incremented by 5 and I is constantly incremented by 1. So that what we can do, we can take the help of one variable and we can remove the another variable. For example, here when I is iterating for 1 to 5, at the time the value of x, right, is just used as a index of a. Instead we can do like this by eliminating one. While x is less than 25 or equivalent to, x is less than or equal, what is the initial value of x? 0. X is less than or equivalent to 25. So when the I value is true until 5, then the a value is 25. If I is 6, right, when I equivalent to 6, that is false, then it is 30, right? So this won't be executed, right? So the x value of 25 we are executing it. While x is less than or equal to 25, then you can write a of x equivalent to a of x plus 1 simply. Whatever the output we are going to get with this loop, we are going to get with the same loop, right? So there, this is called as induction variable elimination, that will help in loop optimization, right? So next one is dead code elimination. So what does it mean by a dead code elimination? A value of a variable is dead if later in the program its value will be read before it is returned to again, right? So or you can go with this definition whatever we have written. Dead code or portion of the program which will not be executed in any path of the program can be removed. No control flows into a basic block. A variable is dead at a point, its value is not used anywhere in the program. No assignment is dead, right? An assignment is dead, value is dead variable. So we have already discussed these flow graphs in the usage count, right? Or there we have discussed tree block. Okay, another variable we have discussed. Okay, let me go with a simple example of it, what exactly this dead variable. So we have already discussed this kind of problem. A equivalent to 10, c equivalent to a plus b, and a equivalent to 20. So d equivalent to x plus y, a equivalent to 30, and e equivalent to a plus y. Assume that we are having like this. So first, how many times a is used here, right? A is defined 2 times. Definition 1, definition 2, definition 3. Here we are using the definition 1. So this is not dead. This d2 is nowhere used here, right? Here we are using x and y. D3, and we use d3 of a. But assignment to this a is dead. So these kind of will be removed. So that is called dead code elimination. So in the next video, we'll discuss about the types of optimization. Of course, we'll be having the same, some kind of same optimization techniques, whatever we have discussed in previous, but in terms of local and global.